Yeah, thanks. So, good morning, everyone. My name is Nils, and I'm pleased to share some insights from the TIMpuls Research Project and the follow-up project TIMpuls Dissemination. This is the large-scale study about fire safety in multi-story timber buildings and the publication of the data. TIMpuls was a joint research project that ran from 2017 to 2021. The goal was to improve the German fire safety regulations for timber construction, especially for multi-story timber buildings up to the high-rise limit. So that means 22 meters highest floor level with a living space above the mean ground level. The project was a collaboration between the 4 research institutions, Technical University of Munich, Technische Universität Braunschweig, Magdeburg-Stendal University of Applied Sciences, and the Institute of Fire and Civil Protection Heiratsberge. It was funded by the German Federal Ministry of Food and Agriculture through the project organizer Fachagentur Nachwachsende Rohstoffe. Co-financing was provided by the timber industry, coordinated by the Bavarian Carpentry Association. One of the main goals was to better understand how different types of timber constructions behave in the case of fire. In addition, the project aimed to develop fire protection solutions that are both safe and reliable. During TIMpuls, many fire experiments were carried out. Small-scale fire tests like the cone calorimeter, medium-scale fire tests like the room corner test, and finally, large-scale fire tests. Today, I will focus on the final full-scale compartment fire tests and how the results were prepared and published in TIMpuls Dissemination. Especially in large and resource-intensive experiments like the TIMpuls fire tests, it is essential that the data is made accessible and easy to understand. This is important not only for researchers, but also for engineers, students, and decision makers. Clear and open data helps others to build on our findings, verify results, and apply the knowledge in the daily work of fire protection engineers. To explain the fire tests and share the results in a clear and open way, we created the website timpulsscience.info. It includes all test data and many visual explanations. So now I will change to the website. So in the next minutes, I will use this website to guide you through the different fire tests. This will give you a detailed understanding of the experiments and the data we collected. In addition, it will give you a clear idea of how to use the website and access the information by yourself. On the homepage, you find an overview about the project goals, research partners, and the founders. Everything I've talked about so far. Now let's take a closer look to the test setup. In total, we carried out 5 full-scale fire tests. As you can see here, the tests were performed in 2 different room sizes. Tests T0 to T22 take place in a smaller room, while the tests T3 and T4 were conducted in a room that was twice as large. All rooms were 2.5 meters high and had 1 large opening, simulate natural ventilation. As you can see here in the overview table, the first test served as a reference and was designed to represent a non-combustible building, such as one made of masonry or reinforced concrete. All structural elements were fully encapsulated with 2 layers of 25mm fire-resistant gypsum plasterboards. Test T1 to T4 used different types of timber structures. These included cross-laminated timber, glue-laminated timber, and light timber frames. Some components with were protected with fire-resistant cladding, others were left exposed to study their direct influence on the fire development. Under the menu item components, you can find detailed information about the construction of each building element used in each fire test. These includes, for example, how the fire load was selected. These included all wall and ceiling assemblies, as well as the element joints between the components. The overview diagrams on the left, so here, help you to immediately locate each component and joint with the test inside. So as you can see like this. In addition, the sections fire load, opening and facade describe the specific boundary conditions for each individual fire test. These included, for example, how the fire load was selected based on the European standards and how the opening area was calculated to simulate natural ventilation. In each test, a 5-meter high facade shield was installed across the full width of the test setup to observe flame spread and temperatures along the external wall. After gaining a general understanding of the test setup, let's take a look at the measuring system. A large number of measurements were taken during the fire tests. In each experiment, between 350 and 380 measuring points were installed. Under measuring, you can find the description of each method used. Air and material temperatures were measured using thermocouples and plate thermocouples. You can see here. The gas flow velocity inside the fire room, at the opening, and along the facade were recorded with bidirectional probes. We also measured the mass loss of the timber frame and the amount of water used for fire suppression. In addition, up to 6 cameras were used in each test to visually record the entire fire scenario. Here in the section measuring points, all sensor locations are shown, including those within the building components inside the fire room and on the facade. The structure is similar to what I showed earlier in the test setup section, which makes navigation very intuitive. Under data download, all measurement data is available for free. Thanks to the measuring point numbers provided in the files and the visual representation on the website, the data can be easily understood and tracked by its original locations. So you can use the data here from the Excel and check them then with the test. For example, here for wall number 2, you can see where the measuring points are be. That brings me to the challenges we faced during the data processing and TIMpuls dissemination. With such a large number of measuring points, preparing and publishing the data was not easy. On the one hand, the dataset has to be understandable and traceable for all users. On the other hand, changes during the construction or test preparation can make this more difficult. For example, in test 1, the ceiling elements were accidentally rotated by 180 degrees during the installation. From a construction point of view, this had no effect, but it means that the temperature sensors and measuring axes were now orientated on the opposite direction than originally planned. This kind of change must be clearly documented to allow accurate analysis and interpretation of the results later on. In short, in real experiments, unexpected things can happen. A cable might be misplaced or a joint design might change. These deviations may affect the data, and that's why they must be documented carefully. To all students here and also my fellow researchers, I would like to say, if you're planning and conducting experiments in your thesis, make sure to plan how you will document every single change. Photos can be very helpful, but they only work if you can still tell 6 months later which component the photo shows. This can be done, for example, by adding short labels to the components, holding a note with a description, or using clear markings directly on the test elements. Good documentation means reliable and traceable data. I hope I've be able to give you some useful insights into the TIMpuls fire tests and show you a way to make complex experimental data both transparent and freely accessible. The TIMpuls Science website shares all this knowledge for others to use, supporting future research, education, and practical application. Thank you very much for your attention, and feel free to explore the website further.